terms that I heard last month at the other MIG conference in Boston that I thought stuck out and really had a lot of relevance to why we're all here today. The first was a quantified self. The idea that we're wanting to measure and quantify everything about ourselves, from the way we walk, the way we sleep, how fast we eat, and so on. The term that's already overused before it actually gets implemented, the Internet of Things. The idea that we'll have computing outside of actual computers with objects all around us. These trends are being driven by the pervasiveness of computing, ubiquitous computing. And not only is there information in the everyday objects around us, but also there's connectivity. So they can communicate amongst themselves and with us. And what wasn't mentioned last month, but as a MEMS guy, a MEMS sensor guy, I thought it was obvious that we needed ubiquitous sensing. And so my talk today is about another addition to the system designer's toolbox called the Micro-Amp Magnetic Gyro, and what it enables system designers to do. So this may be something that everybody already knows, but I thought I'd just spend 1 or 2 slides on some basics just to put everybody on equal footing. The concept of 9-axis sensor fusion is really combining 9 axes of data together to really accurately represent the motion and the orientation of an object. And the way it's typically done is with 3 sensors: the accelerometer, which measures linear acceleration, and since gravity is a form of acceleration, it's often used to measure orientation relative to depth. Then a magnetometer comes in, measures magnetic field on 3 axes. And since we do have this nice magnetic field encircling the Earth, it gives us an orientation relative to magnetic north. And then the gyroscope, which gives us rotational information. So those 3 sensors are the most common sensors that are combined. And again, the idea is to really represent how an object is moving and how it's oriented. So how are these used in systems? Well, the accelerometer has the widest deployment. It's probably the one that matured the earliest, that really is a foundation device. It's used in most motion sensing systems. It controls other sensors, turns them on and off, like we've heard from a number of other speakers. In terms of deployment, these are from a 2012 estimate of over 1 billion accelerometers out there, so there's even more today. And it really does a lot. It controls other aspects of the system, gives you screen rotation, app functionality, and a host of other, is used in a host of other applications. When that's not enough, what's typically added then is a magnetometer. And with that, you also have another 3 degrees of information, and it gives you a sense of orientation relative to the Earth. And I should say that you can't really get a good heading without the magnetometer being paired with an accelerometer, because what you're trying to do is the Earth's magnetic field is not always running parallel to the surface of the Earth, and so the accelerometer is used to extract that projection of the magnetic field parallel to the Earth. And then the gyro, which Tara mentioned, is a great addition. It really gives you a lot more information. So much of the motions that we're interested in are rotations, especially human motions, heads, arms, legs. And so that's also used and gives you another level of information. Paired together, you have a 9-axis system. Now, as you go from just a standalone accelerometer to adding up those 3 sensors, your performance goes up. You have a lot more information, you have a lot more awareness of what's happening. And each sensor can actually compensate a little bit for the other sensor's weaknesses. But with the 3 sensors, your cost also goes up. The accelerometers are by far the cheapest device these days. The magnetometer, second cheapest, and the gyroscope costs the most. Power consumption goes up. Every single talk is talked about power consumption. The accelerometer takes the smallest amount of power. The magnetometer, second most, and the gyroscope requires the most. And that's because it's an actively driven device, typically run at resonance. And So it takes a lot of power to keep it active and do the feedback. And lastly, size also goes up. Not only do you have more sensors, but the gyroscope is generally the largest of the three. So it comes with great rewards, but also with some costs. So what I'm talking about here today is a Micro-Amp Magnetic Gyro. It's an option that fits nicely in the in-between space between having a gyro and not having a gyro. So you want to know about rotation, but you're not sure whether the system can support a full-fledged gyro. So what is it? It's actually a perfect example of sensor fusion. It takes a physical magnetometer, a physical accelerometer, and then some clever software, and combines the information from the two to give you gyroscopic functionality, and to do this at less than a milliamp. So there's quite a few companies promoting this these days. Freescale posted an article recently explaining the theoretical underpinnings of the virtual gyro. IHE Steel has been promoting this for some time. Bosch has mag gyro emulation in their e-compass application. Node and Kionix has their own mag gyro, which is emphasizing performance and low power. So let's talk a little bit about performance. This is one of those takeaways, the slide that I think is very important to know. And it's that performance of the mag gyro is going to highly depend on the quality of its components. It's going to depend on how good the accelerometer is, how good the magnetometer is, and how good the software is. The old adage, you get out what you put into it, is true. So if any of those are suffering, you're really going to get an inferior result. What you really want is high quality inputs, and it'll give you a high quality output. So that's critical because there is a lot of variation in accelerometers in today's magnetometers and, of course, software implementation. So what are the requirements that these sensors need to achieve in order to give you a good result? Noise is by far the most important. The accelerometer should be a low noise accelerometer, probably about 150 to 200 microGs per gigahertz. It's not so hard to find that these days. And the magnetometer equally needs to be a low noise device. And the two need to be of comparable noise levels, because the worst one will dominate the system. And one back of the envelope calculation you can do to get a sense of what's comparable is, since the accelerometer can be used to measure your orientation relative to gravity, you can say what kind of error in degrees do I have with a certain noise level. The magnetometer is the same. It can measure orientation relative to magnetic north, and you look at what kind of degree accuracy you have there, and those two should be about comparable. Otherwise, making one much better than the other doesn't really do much in the system. Another area that's very important is response time and latency. Now, the algorithm is using the data from the accelerometer and the magnetometer, and it's assuming that data is synchronized. Any deviation from that will cause errors in the output and errors in what's really happening in the device that's being measured. So you want to have a latency of less than about a millisecond. Otherwise, you'll probably see a degradation in the gyroscopic outputs. And finally, the software. This is a harder one to put a number on, but it is as important as the others, if not more. And that's because it has to do so much. There's a lot of things that have to happen and to work well in order for you to get a very good gyroscopic output. It needs to constantly be calibrated. It needs to look for and mitigate magnetic anomalies. We're living in a very electrified world, and fields are shifting all around us. We have steel beams all over the place. So good software needs to recognize that and to tease out that constant magnetic north signal in the space that it's sitting, and know where that is, and use that. And it does that by a lot of intelligent filtering and managing the noise levels of the two sensors and the environment, and taking into account when it feels like it's seeing some non-ideal time varying conditions. Now, another thing that the software needs to do is it needs to maintain a proper trade-off between accuracy and responsiveness. A lot of noise and a lot of issues can be solved or made better by averaging, but averaging takes time. And so you have to you have to properly trade off between how long you're going to take to average and when you're going to deliver the output. And an example of that is if you have a slowly rotating device, you can perceive jitter and noise much better than a rapidly rotating device. And so you have time, actually, because it's slowly rotating, to do more averaging, and it actually benefits you more. You have less time in a rapidly rotating device, but it's not as important because it's moving so quickly, you're not going to perceive small errors. And so having an algorithm to properly do that is important. And finally, and also equally important, is you don't want this functionality to come at a huge cost. The whole idea is that you're trying to save on this, and so what you need is a really well-optimized code. It really can't require a lot of resources in the system that's being put in. It needs to have a small memory footprint, and it needs to have a low processing power requirement. Throw some numbers on that. A proper algorithm should take a few, maybe 3 kilobytes of memory and 3 MIPS of processing power. So, put all these things together, and what are the benefits, or what's the reason to do this? This, like I said, is the number one reason. It's the number one reason that gyros are not used or not turned on most of the time. And what you can get is you can get an 80 to 90% power reduction while still getting gyroscopic functionality, still getting rotational output. Numbers will vary. There's a lot of gyros out there. I expect a range of 4,000 to 7 microamps for a physical gyro. Now, looking at what a Micro-Amp Magnetic Gyro is taking, you add up the sensors. How much power are they drawing? Probably on the order of 450 microamps. And then to be fair, you want to also account for the amount of power the processing requirement draws, and that's about 500. So you add those two up, and if you compare a standalone physical gyro with a standalone Micro-Amp Magnetic Gyro, you're getting gyroscopic outputs at 1/5 of the power. But often these things aren't used standalone. Usually they're in a 9-axis system. So a physical gyro, you have an accelerometer, a magnetometer, and then you're saying, I want to add gyroscopic functionality. I want to get that rotational information. So I'm going to add a physical gyro to the system at a power cost of 4,000 to 7,000 microamps. Now with a Micro-Amp Magnetic Gyro, you're saying you're already starting with these sensors there. So you really don't have to count that. So what you're actually requiring in terms of adding this functionality is 500,000 or 500 microamps. Also related to power, not as important but worth mentioning is the operational voltage. Most gyros, not all, but most of them, require a slightly higher voltage than the other sensors. A lot require 2.5, 2.6, or 3 volts or above to operate. The Magnetic Gyro can operate down to 1.8 volts. And so that helps in 2 ways. It gives you a wider range of applications to put this functionality in. And since everything's being run off of batteries, and as a battery discharges, its voltage drops, if you're able to run at a lower voltage, you're able to run longer. So what about the outputs, the rotational information? What are you getting? The Micro-Amp Magnetic Gyro is not a physical gyro. It is not directly measuring rotation, so it will not be as good. But the real question that people who are interested in this would need to ask is, what does your application require? What do you need? Physical gyro, depending on the algorithm and how you're using it, would have maybe 2 degrees of accuracy. The Micro-Amp Magnetic Gyro, you probably could get about 5 degrees. That's our target in terms of accuracy. So is that good enough? It really depends. It will be good enough for some people, it won't be good enough for others. A good example is pointing. If you've got this laser pointer and you're pointing on a wall far away, you may be able to see the difference between 2 degrees and 5 degrees. But if you're trying to measure some body motion, whether a head's looking a certain way, whether you're flipping something over, rotating at 45 degrees, the difference between 5 degrees and 2 degrees is not that important. Another area is zero rate bias. I think Per alluded to this a little bit in his talk, is a lot of times you're integrating this information so that you can get position or orientation. And the gyro does have this zero rate bias where if it's not moving at all, it's still reading a little bit of rotation. And that rotation, if you're integrating, adds up over time to some error. Now, since the Mag gyro is actually using an external reference, it doesn't have a zero rate bias. It always, if you left it sitting for a long time, it would always be pointing in the same direction. Startup time, physical gyros are often kept off in order to conserve power, so they need to be turned on when you want that information. Startup time can be an issue. Physical gyros have, I don't know if you can see it, but typically around 50 milliseconds to 100 milliseconds startup time, because from there, as I said, they're devices that are operated typically at resonance, and so you have to kick it and get it to ring up and then start to equilibrate to a consistent resonance. And that takes some time. The Micro-Amp Magnetic Gyro does not have that requirement, and so it can start up in 10 to 20 milliseconds, as long as it takes to turn the sensors on and get them outputting data. Now, that's assuming you're doing a cold start. If you actually have magnetometer and accelerometer data coming in your system for other reasons, the startup time is essentially negligible. And lastly, size is another advantage that this brings to the table. The smallest NineAxis system that I could find, a single chip solution, with a physical gyro was 4x4, or 16 square millimeters. The Micro-Amp Magnetic Gyro can fit in a package of 3x3 or 9 square millimeters. So that's taking up nearly half the space, imported in a lot of systems where space is a constraint. So the question is, for a number of people looking at this, is the Micro-Amp Magnetic Gyro the right solution? And again, as I alluded to earlier, the answer is it depends. It depends on two things. It depends on what type of functionality, what level of functionality your application is requiring. The assumption is you want rotational information. You may want a NineAxis data set. So what level of accuracy do you need? What level of performance do you need? And then the other side of is what can you support? What are your resources? What are your constraints of the device or the system or the application? And so by looking at those two sides of the equation, what you want and what you can afford, we'll answer the question of whether this is a viable option for your system. So for the rest of the presentation, I was just going to briefly go through 5 application areas and just make a couple of comments about the applicability of this Micro-Amp Magnetic Gyro. So we've already seen, I think, all 3 of these images, but it's because they're very much in the news. People are really familiar with it. There's a big business starting in terms of measuring activity. But that activity is not that sophisticated. They're really trying to just gather count and do some basic things. And as far as I know, none of them use gyros because power is so critical. These devices want to be on nighttime, daytime, while you're sleeping, while you're awake. So that is an issue, and that is really why, although they would benefit from rotational information, they're not using it currently. If you could use it, you could do a lot more sophisticated things. You could measure motions. You could measure form. I mean, imagine measuring your golf swing or your tennis racket swing, or you're doing exercises and how good is your form there. So there's a lot that could be done if you could include this sort of functionality in your devices. And then also with gesture recognition. These devices have a minimal user interface. And so what you're wanting to do is you want to interact with these devices directly, but you don't necessarily have a touchscreen or other large number of buttons. And so you can implement some gesture recognition to get a little bit more natural interface and more options. Headsets, headphones, helmets, these things that we all wear on our head. This is a perfect application area for rotational information because all of our head movements, left, right, up and down, they're all rotations. Now, why would you want this or what could you do with this? User interface is one area. You could be talking on a phone with a headset on, have another call coming in, you nod yes to accept or nod, or swing your head no to reject. In terms of pointing and viewing, you often could present information depending on where someone's looking or where someone's listening. Or motion recording. It could be a picture of ski goggles here. You could be going down the slopes hit a jump, do a helicopter, and you want to show that to your friends. So lots of reasons, lots of uses, but all these things are meant to be on our head, and so you want it to be as inconspicuous as possible. You don't want to have a big battery sitting there, because battery weighs power. You want it to be small. If you're trying to make something like this, you really want it to be a minimal, almost invisible component that's there. And so power, size, weight all matter. So again, hits upon some of the strong points of the Micro-Amp Mag Gyro approach. Smartphones, another area that is, it's the 800-pound gorilla. It's the one that's pushing all sensor mainstreaming. To this day, there's still a huge number of smartphones, mid-range smartphones, where the physical gyro is not used. It's not used because it's just too expensive. It's too expensive either in cost or in power consumption. And so this is an interesting option because at the same time, NineAxis functionality is being propagated to phones on a widespread basis. And so getting this NineAxis without the gyro is of great interest to a lot of companies. Now, with the top tier smartphones, they'll definitely have gyros in it. It's almost a standard component these days. But that doesn't necessarily mean that you won't want this Micro-Amp Mag Gyro capability. Because if you have a physical gyro and you pair it with a Micro-Amp Magnetic Gyro, you have this option of intelligently trading off power and performance. You can run at a lower power cost the Micro-Amp Magnetic Gyro for most of the time. And then when you identify situations where you really do need that bump in performance, then you power up an actual physical gyro. And when you do that, you can actually have enhanced performance for that physical gyro because the Mag Gyro could offer some bias and sensitivity calibration. So it's an interesting concept to not be an either-or proposition, but be either-or for both proposition. Wearable electronics, it's not that mature yet, but there's a huge amount of work and a huge amount of interest, again, embedding sensors in objects that we wear all around us, whether it's gloves, smart clothing, footwear, earbuds, rings, jewelry, watches. The applications are plentiful, and the uses are widespread. You may want to just track that motion, as we talked about before. As other people have been mentioning in previous talks, contextual awareness, knowing what's happening in the person so that certain reactions can be made, certain information can be gathered. Novelty effects, I think, is one of those ones where there's a big market because imagine if you could have something happen when you shake or when you wave or when other things happen. And I think about this as, for some reason, thinking about sneakers, I never thought that the flashing lights on sneakers would be so widespread, but it seems like annoying. But the fact that it sells is of interest. So novelty effects, I think, is not a small market. Embedding that is probably one of the earlier areas that will gain some of this wearable electronics functionality. And finally, again, gesture recognition. And lastly, handheld objects. Again, so much of our motions are rotations about pivot points. So sports equipment is right. Your tennis swing, your golf swing, a bat, a lacrosse stick. There's so many areas in sports where you want some rotational and motion tracking information. In toys and in games. I think everybody's familiar with that. In key fobs, there's actually a fair amount of interest now making key fobs a lot more intelligent and embedding some more functionality in those. And so there's an awful lot of application areas, and all of these want to use motion tracking. They want to embed some novelty effects or some interactivity where there used to not be any, or using motion sensing and rotational information to help with the user interface. So, in conclusion, the parting thought is that what I hope I've conveyed is that there's this space in between not having a gyro and having a gyro. And that space can be filled with the concept of the Micro-Amp Magnetic Gyro. It really offers a number of things. There are certain systems which absolutely need gyroscopic functionality. And so now you have the choice of either going with a physical gyro or a Micro-Amp Magnetic Gyro or both. And there are certain systems where a gyro is just not a feasible option. And so this gives the developer or the system designer that option. And finally, because it works within this this evolving and infrastructure of NineAxis data, this thing where everybody's starting to gain familiarity and building tools, it should integrate relatively easily. So thanks. Like I said, our target right now is about 5 degrees, but again, it really depends on, oh sure, the question was, is there a hard limit on the accuracy that can be achieved? And no, we don't know of a hard limit. Right now we're targeting 5 degrees as acceptable performance. We want to go better, but it really does depend on the noise levels of the components, like I said, and the algorithm and the environment that it's in. Yeah. Okay, so I think you were at, I'm not sure I entirely got the question. Are you asking about the, can you repeat it?
Yeah.
Okay, yes.
The consistency in the user experience.
Right.
So
So what you're saying is basically like an accelerometer, if put level and moved, the outputs don't change, right? X and Y are still seeing 0 degrees. And again, if you align a magnetometer right along the vector of the magnetic field, you really can't tell as it spins around that. So how does that affect it? It is a limitation of the system. Now we're assuming these systems are generally moving, and so that's not a constant situation, but it is certainly, I would say, just an intrinsic factor on this application. You can't get around the physics of it. But the question is, how often are you in that very aligned state? And so.
One more question? Oh, what? You asked a bunch. I know I saw. I'm sorry. There was one in the back. I thought I saw. Okay. All right. All right. I'll let you go. Stand up. Stand up. Stand up.
So what's the degrees per second can measure since it's using an accelerometer and mag? Pretty slow.
No. Actually, if you do the full range, I mean, we typically, gyros these days go up to about 2,000 degrees per second. And you can measure 2,000 degrees per second with this as well.
All right. Let's thank our speaker because we have one more.